back to Python for Machine Learning. Let's do some digit recognition. This is the QR code which points you to the website and the GitHub repository with these slides and all the other material. So, our task is handwritten digit recognition. On the right hand side you see some samples of digits that were written for postal codes for the US Postal Service. They collected this data and made it available as a test set. So the input image is a grayscale image. It is 28 by 28 pixels, is web reserves, so it's pretty small images. And it has 255 levels of gray values. The output data is of course a digit 0 up to 9. There is a set of training examples and a test examples. So the set of training examples will of course be used only during training. The set of test examples will only touch as soon as we're done training to assess the real world applicability of our algorithm, of our trained neural network. So the first task is to explore the data a little bit and to see whether there are interesting things to be discovered there. So before starting any machine learning task, it's a very good idea to explore your dataset. So let's do so. We need a few Python modules in order to do that, and especially MNIST. That is one of the datasets that comes with keras, and that's the dataset which we will be using. We also need matplotlib, numpy, and counter from the collections module of the standard Python library. So the first thing to do is to load the data. So the MNIST dataset comes with keras and it returns two tuples, one for the training data, the other for the test data. The first element of each tuple is the input, xtrain, xtest respectively. The second element of each tuple is the output, so ytrain and ytest. It is actually downloading the data. This is cached, so normally it happens only once. Okay, then let's determine the shape of the input and the output. So let's start with the input. We check the shape, the D-type, for the training set input and output. So we've got in total 60,000 training examples. They're each 28 by 28 pixels, and the D-type is uint8, so that's grayscale values 0 to 255. For the output we have also obviously 60,000 values, and the D-type is also uint8, which is of course fine to represent numbers from 0 to 9. We can do the same thing for the test set, and there are 10,000 similarly shaped and typed examples in the test set. So let's have a look at the semantics. Let's visualize one of the inputs for the training. So as you can see, this actually represents the data which we expect. So this is a handwritten digit 5. So indeed there are 28 by 28 pixels. We visualize that using matplotlib's IMShow, so the image show. We can check the corresponding output value, and that would indeed be the number 5, the integer 5. Okay, we can do something similar for a number of plots. So for the first 25 inputs, that would be not the first 25, that would be the first 35, I guess, whatever. But basically you see that we actually get the digits in grayscale, and that the corresponding outputs are indeed what we would expect. So this is our training set. So the input, grayscale images, 28 by 28 matrices, the output, digits from 0 to 9. Let's also check the distribution, because perhaps some digits are overrepresented, some are underrepresented. So it's always a good idea to check that. And this of course we can do by just counting the training data, the output, and bin it by digit. And yeah, it's fairly uniform. So the digit 1 is somewhat overrepresented, the digit 5 somewhat underrepresented, but this is reasonable. Let's also check the same thing for the test data, since of course we would have to know whether things are more or less representative, and indeed we see a very similar distribution, with again the number 1 slightly overrepresented and the number 5 somewhat underrepresented. But in general this looks pretty much okay, pretty much uniform. So now we can start on our actual training of a neural network. In our first approach, we'll represent the data as a one-dimensional array. So rather than as a two-dimensional image, it will just be a one-dimensional array. So essentially, we just put one row after another into a long one-dimensional array. The output data is not the number itself, but rather we switch to a one-hot encoding. So basically in this case, the sixth element of that array would be 1, all the others would be 0. So that's the data types. Also we switch for the image from the integer representation of the grayscale value, so from 0 to 255, we rescale that image or those values between 1 and 0, and they will be floating point values, single precision, so float 32. The model which we'll use is a multi-layer perceptron, so a feed-forward network with a number of layers. We will have 758 inputs, that's 28 times 28. This will be fed into a dense hidden layer with 512 units. So dense means that all inputs are connected to all outputs. The output of these 512 units will be fed into an activation layer, and the activation function which we're going to use is a rectified linear unit, a ReLU. The output will be used as input into another layer, again with 512 units, another dense layer, so each of the outputs through the activation function of the first layer goes into the second layer. Again, this is dense. For the output of those second layer units, we again use a rectified linear activation function, and we feed the output into the input of a third dense layer, but with only 10 units. So each of these 10 units represents a specific digit, and we use as activation function a softmax to ensure that we get a probability distribution over each of the potential outputs of that unit, so basically over each of the 10 possible digits. So let's program that multi-layer perceptron using keras. So we import keras, we import the MNIST dataset, and we also import some other things, like for instance from sklearn model selection we import train test split. We'll see what that is good for. As you can see, we also import quite a number of things from scikit-learn because we want to set up a proper pipeline in order to deal with our data, our training data, and matplotlib in order to do some plotting. Okay. Reload the modules, and just like before, we load the dataset. This time it has been downloaded, it's already cached, so it's immediate. Now we need to transform the data. So first we need a reshaper. So we want to reshape the data from a two-dimensional 28 by 28 array into a one-dimensional 758 one-dimensional array. Okay, so we use a function transform for that. And we also want to normalize the data because, as you know, it's 0 to 255 integer, and we want a 0 to 1 floating point. So again, we just use a function transformer for that, and we create a lambda function that simply converts the data first into a floating point value and then divides by 255. So we combine both pipelines together into, both transformations together into one pipeline. So we use the scikit-learn pipeline constructor for that. So the first one is the reshaper, and the second one is the normalizer. So we specify our pipeline components as tuples. The first tuple is the name of the component, the second is the actual component. Okay, now we can fit transform our data, so that is for the training data, for the input. And note, for the testing data we do almost the same thing, except we do a transform rather than a fit transform. We discussed that in the scikit-learn part, why that is important. Then of course we also need to have the output, and again we're going to reshape it first, and the encoder in this case is a one-hot encoder, and the categories are auto. Basically we don't care, it's just 0 to 9, and again we want the output as floating point values as well. So that's just an S type. We assemble the output, the pipeline for the output. So this has three components. First the reshaper, second the binarizer, and then the type changer. And we run the training set and the test set through that pipeline. Just to check, the output training is now indeed 60,000 examples, but 10 columns wide, so one for each digit. Just to check, indeed the first training example is 05, so basically this is a sparse notation. So scikit-learn is smart enough, if you do binary encoding, to give you a sparse representation rather than a dense representation. This saves up a lot of space, so it's quite important that you actually do that, or that scikit-learn does it for you. And keras can actually deal with sparse data as well as dense data, so it doesn't matter. Alright, so we have our training set, but actually we want to set apart a number of examples in the training set as validation set. So those will be used in order to assess the accuracy during the training process, so that at each epoch we know how the accuracy has been improved on data that was not involved in the training set. So since this will involve a random selection out of the training data, for reproducibility it's quite important that we now set the random number seed, and we do this to some value, but it's important to remember to do this. And the second thing we want to do then is to split our training set into two parts, one set for training, the other for validation. Both will be used during the training process. The training data will be used to actually compute, using the backpropagation algorithm, the weights for our neural network. The validation set will be used during training for the assessment of the training process. We can easily split a data set into training and test by using a utility, train test split, and that takes input data and output data and returns four data sets. The input values for training and validation, the output values for training and validation. Let's check the shape, and basically we have 45,000 examples now for training and 15,000 for validation. And the dimensions are right, so basically we have 28 times 28, so 748 for the input and 10 for the output. Okay, of course we have done quite some manipulations, so at this point it might be smart to just check whether things still are still okay. So we reshape the first training example into a 28 by 28 and we visualize that. And as you can see, we still get a number. Of course it's not necessarily the same one as we had before, because we have selected some examples out of the original training set and into the validation set. So it's okay that this is of course a different number than before. Let's check whether the output checks out. So indeed the sparse representation is indeed for 6. So that's good. We have the data in the format we want. And it's time to set up our neural network. So this is a classic multilayer perceptron, but we are using keras in order to define that. So we need quite some stuff from keras. We need a model, and that will be a sequential model. That basically means it's a feed-forward network, no recurrence. We need some layers. We need a dense layer, we already know what that is, and we will also use a dropout layer. So a dropout layer is intended to avoid overfitting. It will just randomly reset a number of weights to 0, a fraction of the layer, and this is to avoid overfitting. We also need an optimizer, and we will use an SGD for that. And as a metric, we want a confusion matrix. And we also will do some direct things with TensorFlow, so we import TensorFlow as well. Again, it's important to set the seed. I'm actually doing this again, because if I would have re-evaluated a few things in the previous section, then this might actually, for instance, if I would have split the set, the training set twice, that would have an influence on the random number generator here, so it's better to again set it here. And also note that it's important to set the TensorFlow random seed as well, because that would be independent from the one which is used by NumPy and hence keras. Okay, so first we define our model, it's sequential, and then we start adding layers one at a time. So the first layer we add is a dense layer with 512 units. The activation function is a ReLU, so rectified linear, and the input shape is 784. So that's the size of our input data. The next layer we add is again a dense layer, again 512 units, activation function is ReLU again, but we don't specify the input shape. The input shape is just inferred by keras from the previous layer. The previous layer has 512 units, so that's 512 inputs for the next layer. And then we add the third layer, which is again a dense layer, but this time only with 10 units, and a softmax activation function. We can ignore the warnings, that is for future fixing by the keras people. Model summary. So this is always very useful to run, since it gives you a good overview of the number of parameters your model actually has. So we have 512 dense layer, that's our first layer, 512 dense, that's our second layer, and then 10. And actually the numbers add up. Let's start with the third layer, so dense 3. As you can see, it has 5130 parameters. So why is that? Well, basically we will have 512 inputs from the previous layer plus one bias unit, so that is 513, and we have in our layer 10 units, so that's 10 times 513. And you can do a similar calculation for each of the layers. So essentially for the second layer we would have 512 units. Those would each have 512 inputs plus one bias is 513. Hence 513 times 512 would be the 262,656, which you see there. And similar for the first dense layer. There of course we would have 784 plus 1 times 512. So this was the model definition. Now we can compile it, and we have to specify which optimizer we are going to use. So here we use SGD, stochastic gradient descent, and the metric which we'll use is the accuracy. So that will be used in order to score the model in the different epochs. And as a loss function we will use categorical cross entropy. So basically that's a good measure for the classifier which has different categories. We again ignore the warnings, and we can actually start training the model. So we want to keep track of the history, and we do model fit. You would recognize that from scikit-learn, but apart from the input training data, xtrain, and the output training data, ytrain, we also need to specify a number of parameters. So an important parameter is the batch size. This basically means it's the number of training examples that will be used in order to do a single update, a single backward update of the model. So we'll actually split our 45,000 input examples into batches of 128 each. We want a maximum of 100 epochs, so basically we want to run through all the 45,000 examples 100 times maximum. We want some verbosity, and the validation data is set to the validation data we split off the training data in the first place. Okay, so this will actually take quite a while. Again, ignoring the warnings, you see that the first epoch is now completed. It is now working on the second epoch. This is happening on a single core of a 2.5 gigahertz CPU. So this would take us quite a while, so it's actually time for dinner. After some time, 100 epochs later, we see that the accuracy on the training set is 99% and on the validation set 97%. So that looks quite reasonable. Since we saved the history, we can actually plot results, and for that we just define a function that takes the history as an argument and does some plotting for the loss and for the accuracy. So the first plot is the loss function, and as we can see it's lower for the training than for the validation data, which is quite normal. For the accuracy we see the reversed. The accuracy for the training set is of course higher than that for the validation set, so that's pretty obvious. Now let's check how this is doing with respect to scoring. So indeed we get 99% accuracy on the training set, and on the validation set we get 97%. Let's see how it's doing on the test set. And that is 97% as well. So that's actually pretty good. We can save the model to an HDF5 file very easily by just model save and the file name. This is nice because we can reuse it later in order to use it on production data. One of the things we might try in order to improve the outcomes are to add dropout layers. So one of the risks with backpropagation in general and neural networks is that you overfit. To avoid overfitting, one can add dropout layers, which basically remove a fraction of the weights, set them to 0 randomly. So our model looks fairly similar as before, only between the first and the second dense layer we add a dropout, and we also add a dropout between the second and the third layer. Ignoring the warnings as usual. The summary of course is quite similar. The dropout layers don't add any parameters. We can compile the model, similar as before, and we can run it again using fit and see how this affects the accuracy. Again, this will take quite a while on this one core of my CPU. 100 epochs later, it turns out that the accuracy on the training set is a little lower. It's only 98%, but the accuracy on the validation set is slightly higher. Not much, just a little bit. So again, let's plot the history of the model. And again, conclusions are similar as before. So let's check the training error. And the validation error. And the error on the test set. And as you can see, it is indeed a bit better than before. So obviously Dropout helped us to avoid some overfitting. Again, we can save the model for future analysis. In order to understand the model, it might be nice to actually check it a bit, what's going on. And one way of doing that is by computing the confusion matrix. We've already seen a confusion matrix in action in the part on scikit-learn. So let's do that again. We import a few tools in order to help us with the tools pandas and seaborn, a nice package to make plots of a statistical nature. So what we will do is we will extract the predict classes for the test set as well, and we create a color map to a confusion matrix rather, to show us what is going on. So basically the values on the diagonal are very high, which means that the model is quite accurate, as we already assumed. So we see some off-diagonal values which are not very high, so there is some major confusion between 4 and 9, which is kind of understandable, and there is also some confusion between 5 and 9, which is again kind of reasonable. However, it's better to just visualize that, and we define a function to do this, and we can then use that to plot the confusion matrix in a much more visual representation. And then of course it is pretty clear where the confusion lies, and we see that we have some confusion between 4 and 9 indeed, and between 4 and 9, which we already had, and 5 and 9, and so on. So this is a good way of testing the performance of the model in a higher level way. If you have the compute capacity, it's also interesting to have a look at how the model behaves when it is when it gets different inputs as values. So basically this is an analysis which I'm not going to do, but the code is here and is available in this notebook, which is in the repository. In the next video we'll have a look at deep neural networks.